Okay, so last time we started looking at the least squares problem in the case of linear regression. But now we want to return to the general least squares problem. And you'll recall that it looks a little bit like this. We want to minimize over all x in Rn the L2 norm squared of the difference between y minus ax, where y is some vector of m samples, a is an m by n matrix, and x is a vector in Rn. So in the case of linear regression, when we just had two parameters to fit, we were able to just derive a 2x2 system of equations that we needed to solve in order to find a solution. And now we want to do something similar. So you recall that in the case of linear regression, what we needed to do was take derivatives and set them equal to 0. Here we're going to do the same thing, but now we have n parameters we need to worry about, and so there are n partial derivatives that we need to set to 0. And so the natural way to handle this is to take our objective function and compute the gradient. So you hopefully remember that the gradient of a function f is just given by the vector of partial derivatives of f with respect to all the different variables, which we write as follows. And what we're going to want to do is to set this equal to 0. So what is the gradient in our problem? We want to compute the gradient with respect to x of the norm of y minus ax squared. One way of doing this is using the chain rule, which we work out carefully in the notes. The idea here is that we can write our objective function as h of x and realize that h can be written as the composition of two simpler functions, f and g, where f of x is just x transpose x, and g of x is just y minus ax. Both of these have simple gradients. It's relatively easy to see just by writing out these expressions, but they're also worked out carefully in the notes that the gradient of f is just 2 times x, and the gradient of g is minus a transpose. So using the chain rule for h of x, we have that the gradient is just going to be given by the following, which in our case is going to be given by minus a transpose times the gradient with respect to x of f. So this would be 2x, but now it's going to be evaluated at g of x. So y minus ax. And just doing some rearranging, we obtain the following gradient. Now we can set this equal to 0. We can divide both sides by 2. And then just by simple rearranging, we obtain the system a transpose ax equal to a transpose y. If a transpose a is invertible, this means the solution to our optimization problem can be written as a transpose a inverse times a transpose y. This is one formula for what is called the pseudo-inverse of a. It's often denoted by a dagger. And as long as a transpose a is in fact invertible, this does indeed provide the optimal least squares estimates, i.e. the solution to our original least squares problem of minimizing this function that I'm calling h of x here. Based on analogy to the 1D case, maybe you're already satisfied that if we can find a vector such that the gradient of the function vanishes there, that must be the minimum of our objective function, this least squares objective function we're trying to minimize. But I want to provide just a little bit more of a careful and rigorous justification for this, partly because later in the course we're going to generalize this argument to arbitrary convex functions, and I think it's nice and simple in the least squares problem. So to do this, let's let f of x denote our objective function. And recall that we can also express this as the inner product between y minus ax and itself. And if we just expand all of these terms out, we obtain this. And by using simple properties of the matrix transpose and collecting similar terms, we realize we have something that looks like y transpose y minus 2x transpose a transpose y plus x transpose a transpose ax. So we'll use this fact in just a minute. Now, remember what we're trying to do here. So we're trying to show that the x hat we found earlier is the minimum of this objective function f of x. So suppose we look at f of x hat, where x hat is a vector such that the gradient evaluated at x hat is equal to 0, and then we're going to consider a small perturbation u. What we want to show is that if this is true, then x hat must be a minimum, which means that f of x hat plus u must be greater than f of x hat for any possible u. So if we can show that this condition that the gradient equals 0 implies this inequality, then we've shown that this condition implies that x hat is a minimum. To do this, all we have to do is use this fact that we established above, but now instead of applying it to x, we're going to apply it to x plus u. And if we just keep the y minus ax terms together and expand those out, we have y minus ax transpose y minus ax. Then in the middle we have these cross product terms, and then we have au transpose times au. And just rewriting this in the following form, what we see is that we have f of x right here. And then we also have another term that we recognize. This is in fact the gradient of f evaluated at x. So if we just rewrite this, what we've shown is that f of x plus u is equal to f of x plus u transpose times the gradient of f evaluated at x plus this other term, the norm squared of a times u. But since we're only interested in getting this inequality, recall this is what we wanted to show, all we have to do is observe that the norm of a times u is always greater than or equal to 0. So this gives us an inequality that looks like this. And at this point, to establish the results that we wanted, namely that the gradient of f evaluated x being equal to 0 implies that we have a minimum, well, we realize that basically we have exactly what we want. So if the gradient of f evaluated x hat is equal to 0, then that means that f of x hat plus u has to be greater than f of x hat plus u transpose times 0, which is just f of x hat. So that's saying, in other words, just maybe rewriting this, f of x hat is less than f of x hat plus u for all u. Does not matter what u is, u transpose 0 is always going to be 0. So this is always going to give us this inequality no matter what u is. So this is a slightly more rigorous justification that this setting the gradient equal to 0 is a good idea. And this gives us a slightly more rigorous justification that the formula we derived earlier is in fact the solution to the least squares problem. Of course, there were some caveats to the solution that we gave. So in particular, I assumed that A transpose A was invertible. You might wonder what happens when A transpose A isn't invertible, how you might handle this case. To really appreciate what happens in that case, we're going to need to review something called the singular value decomposition, which is what we'll start with next time.